Hello everyone. This is our lecture number 16 and we will be today talking about a very interesting concept in linear algebra which is change of basis. As you remember in our last lecture that whenever we have a subspace then we have its dimension which is the number of vectors in its basis, and every subspace is associated with a basis. The number of vectors in bases is always constant. However, the bases are not unique. The basis vectors can change. The only condition on the basis vector is they should be linearly independent from each other. So we can find many choices for the basis vectors. So for example, let's say we have a R cube, a three-dimensional vector space. Now its basis should contain three vectors, okay, and each of them should be of three components. Now these, which three are the best ones? So I can have, for example, ABC, you can have XYZ, and both are legitimate basis vectors. The reason is because both of them are linearly independent and they are three in count. So it means you are right and I'm also right. But in some practical situation, what happens is that one of the bases has an advantage over the other bases. For example, in image compression, there are certain kind of bases which we call them DCT cosine transform, or we can say Fourier transform or wavelet transform. Um, so these gives you different bases. Although they don't change the number of basis vectors, but they change the basis vector themselves. So which one is better? It depends on the application. However, here we will know how to change from one basis to another basis. So as far as a vector is concerned in linear algebra, when we say its basis, in actually what we mean is its coordinate system, the system with respect to which it is defined. Okay, so when we change the basis, we are changing the coordinate system. Okay, so most of the time, um, so let us say that we have somebody whose name is, so Alice wanted to describe her vector to Bob. So Bob is standing at a distance and Alice is on left, Bob is on right. Now Alice has this vector and she wanted to describe that vector to Bob. Now the way to describe it, definitely she would like to know in which vector space this vector is lying, and based on that vector space she will find the basis, and then with respect to those bases she will define that particular vector, because this vector will be a linear combination of the basis vectors. Okay, so for this she need to define her basis, or she need to declare her basis. So let us say her bases are a1 and a2. So this particular vector, this black one, black arrow, is described as 2 times a1 plus 1 times a2. So this is the linear combination, and this is the description for this vector with respect to these two bases. A1 and a2 are the basis vectors. They constitute the basis. Okay, so for this black vector, these two are basis vectors, and it can be described as 2a1 plus 1a2. Or in the language of matrices, we usually write it as 2, 1 as a column vector. So this vector is represented by a column vector, which is 2, which is the number associated with a1, and 1, which is the number associated with a2. So this is 2, 1. But keep in mind this column is with respect to this basis A, which is the basis of the Alice. Now, what happened is that she sent this particular information about her vector to Bob. So when Bob received the Bob receives 2, 1. However, Bob is using a different kind of basis. He is using the basis set, which is B, whereas Alice was using the basis set, which was called A. So now there is a difference between A and B. So that's why, although the coordinates are 2, 1, still for Bob, it is a very confusing matter, because now Bob will describe 2, 1 with respect to his own basis. So when he does this, what happens? Now let's look into this situation. For him, the vector came out to be the one on this side. Now here, there is a big difference between the vector drawn by the Bob and the vector drawn by Alice. Alice vector is in the third quadrant, where we can see by some means this vector, which is the Bob drawn, is fourth. Although Bob is also correct because he is drawing 2, 1, and Alice is also drawing 2, 1. But since their bases are different, so they are displaying completely different vectors. Okay, you see, because for him the bases for B are G1 and G2, whereas for her the bases were A1 and A2. So since the coordinates are 2, 1 and 2, 1, so when he draws 2 and 1 with respect to G1 and G2, so his vector is 2G1 plus 1G2. When he draws it, it came out to be on this side in the fourth quadrant. So this basically gives you, you see. So now for him, for Bob, what Alice was describing was this vector, whereas Alice was having actually originally this vector. So it means the vector representation, the vector has been completely changed. Whereas what we want is that the representation should change, but the vector should remain where it is. We want the vector to be in the same position where it was with the Alice. So it means that what happened was, when the vector was sent as a column vector to Bob, the bases were not sent. So that's why there was a confusion. So whenever we wanted to send some coordinates, we have to send the coordinate system so that everybody should know what we mean. Okay, so we need to have a change of basis. So we need to, when we want to communicate with Bob, Alice want to communicate with Bob, she has to communicate it with the language that Bob is using, and that language is the basis B. So she has to describe the vector in the language of Bob, which is the bases that are being used by the Bob. She need to send the coordinates that actually are the coordinates of the basis B, whereas she is sending the coordinates of her own basis. So what we need is actually a change of these components based on which basis the other person is going to display them. So this needs change of basis. So let's look into this change of basis now. Okay. So in order to do a change of basis, the first thing is, let us say we wanted to change the Alice basis, which is A, into the bases that are being used by the Bob. So Bob bases are G1 and G2, which are represented by this blue ink, and the Alice ones are A1 and A2 with the red, and there is an angle of 45 between them. So we don't care right now about the angle, but what we want to tell you is that the Alice um, bases are not the same as the Bob bases. So in that situation, what we will do, in order to convert Alice bases into Bob bases, we have to take each basis. So here is A1. A1 is the first basis vector that is being used by Alice, and we will describe A1 in terms of G1 and G2. Then we will take A2, which is the second basis vector used by Alice, and we will describe A2 as a linear combination of G1 and G2. So once we do this, the situation is pretty much, I will just take you to the conclusion, okay? And here it is. So now our A1 is 1, 0, and with the help of this matrix Q, which is a basis change matrix and is written Q and underneath A and this arrow to B. So it means A basis is converted to B basis. We will get new coordinates, but these new coordinates will be with respect to B. So in order to find this change of basis matrix, we will use the technique that we just tell you. Okay. So now here it is. This particular two entries in this matrix are the entries which I told you earlier that you will describe the A1 basis as a linear combination of the Bob's basis, which was G1 and G2. Similarly, you will take the A2, and for A2, you will describe or you will represent A2, which is the second basis of LS, in terms of G1 and G2, which are the basis of the Bob. So once you have it, we'll put those values here. So now let's fill this. So what we find out is that 1 over square root 2 and 1 over square root 2. This is the linear combination for representing the A1 in terms of G1 and G2. Similarly, here the entries are in the second column of this matrix Q, 1 over square root of 2 and minus 1 over square root of 2. So this basically represents A2 in terms of G1 and G2, which are the basis of the Bob. So now we have this matrix. Once we have a matrix, then every vector which is defined in LS basis using this matrix multiplication, we will be able to convert it into new coordinate system, which will be understandable by the Bob. Okay. So here it is. Now imagine you wanted to come back from Bob coordinate system or the Bob basis back to LS basis. If you want to do this, you have to do this inverse thing. So when you do Q inverse, the same matrix, but this time you take the inverse of that matrix and you will get B to A. So this matrix, inverse matrix will give you B to A, whereas the forward matrix will give you from A to B. So it will take you from A to B, and on the way back, you need to do Q inverse. So this is the situation that you will mostly encounter. So you see Q inverse, the arrows are from B to A. Now you will take any vector in B coordinate system or in B basis, and you wanted to convert them into LS basis, which this is the one LS basis, then you have to use what is known as Q inverse. So if you take this Q inverse matrix and multiply it with this vector, you will end up with a new vector, and that new vector will be with respect to basis used by LS, which is A basis. Okay. So now everything is very clear. So this is called linear transformation. So linear transformation is basically you take an n-dimensional vector and you get another n-dimensional vector. But keep in mind, what you are doing is you are changing the coordinate system. So the coordinate system is changing, whereas the vectors remains where it is. Now, you will be wondering that in previous lecture, we say whenever a vector is multiplied with a matrix, it actually changes that particular vector or transforms it. The same thing is happening, but here the perspective is that the vector remains whereas the coordinates transforms. So coordinate rotates or shrinks or whatever. So here the vector remains at the same position, but the coordinates changes. In that case, the coordinates remains and the vector changes. So when we say that a matrix multiplied with a vector has changed or transformed the vector, in that case, we are still remaining with the same coordinate system. But the same thing can be said in a completely different way. And the new way is that when a matrix multiplies a vector, the vector remains, whereas its coordinates changes. So saying both ways is okay, but this is just the perspective of how you say it. So when you say it in the second way, it means that you're talking about change of basis. So you're talking about change of basis matrix, okay? So let us say we have a matrix, we have a vector in B basis, and we wanted to do some transformation or some processing on it, which we call M small b. But we are not able to do it quite conveniently. So what we do is we take this B, and we feel that it is a lot easier if we can do it in A basis. So in order to do the processing in A basis, first we take this vector and we'll take it to A basis, do the processing, and then do inverse and bring it back to B basis. In order to do so, we will be doing this. First step is Q inverse. So once you do Q inverse, you are taking the vector in B and make it a vector in A. By this particular Q matrix multiplication, Q inverse rather, multiplication, you got the same vector that was there in B basis, but this time the basis become A. So this is a transformation from B basis to A basis. And then you do the processing because you are inside the A basis. So you do the processing which was defined with respect to A basis. And after this, what you will do basically is that you will apply the inverse basis. So now you have this MA processing, and now you got this dot dash in A. It was before dot dot. So after processing, it become dot dash, but they still have the same basis. So the processing did not change. It just changed the coefficient, but it does not change the basis. So the basis remains same. And now you will apply this Q again, because this Q will take this vector, which is in basis A, this processed vector, which is in basis A, and bring it back to basis B. So in order to do the completion job, you will do Q and you get B. So now you got it processed in A, but you played a trick because the direct processing was kind of inconvenient, hard. So an alternative way is you did Q inverse, you brought it into A, you process it, MA, and then you brought it back to B. So you can go this direct way of processing in B basis, or you can do this indirect way of Q inverse, then processing in A, and then Q, and then bring it back to B. So sometimes the alternate way is more convenient. So that is why we just have this notation, and that notation is Q, then you have a processing, and Q inverse. So keep in mind, if you see these three matrices, that basically means that the processing is done in the alternative way. Okay, so this is one particular usage of change of basis, where change of basis becomes really a convenient step in processing vectors, which cannot be processed in their original coordinate system or in their original basis. So they have to be transformed into another basis, processed, and then bring it back. So thank you very much for listening to this particular lecture. And if you have any questions, please comment in the YouTube, or you can also send me uh, emails or Google Class, so on. So we'll talk about it next time, a very important topic, which is eigenvector and eigenvalues. But keep in mind, eigenvector and eigenvalues are both directly linked with the change of basis. Okay, and they are eigenvalues and eigenvectors are actually basis, but a particular kind of basis. Okay, so thank you very much, and we'll see you next time. Take care. Bye bye.